classroom. I think I have also provided some video links on these concepts. So we will continue with the discussion. So I want to cover today, I'm going to discuss about dynamics. So as we have discussed, kinematics deals with the relation between position, velocity, and joint variables of the robotic system, right? So as you have seen, if it's a revolute joint, theta of t is the joint variable. If it's a prismatic joint, the displacement is the joint variable. And so what is its position, what is its velocity? So to reach a certain position, what should be these values of joint variable? Okay. To achieve a certain orientation, what should be the values of these variables, joint variables, or even the values of the joint variables, what is the position and orientation? This information we can get by the kinematic model of the robot. But in this kinematic model, we do not consider the forces and torques that actually cause this change in position and change in velocity, right? So that part is discussed in, or that part is modeled in what is called the dynamic model of the robotic system. So in the dynamic model of the robotic system, we will have the mathematical equations that include the terms involving force or torque, whatever is causing the change in position and change in velocity. So why do we want to do a dynamic modeling of a robotic system? What is the use? It can be used for computer simulation of the system. Okay. So once we have the mathematical model, we can implement those equations in MATLAB. Okay. Then apply whatever the signals, force signals. Then see the response. What is how the position is changing, how the velocity is changing. So this kind of simulation we can do on the computer. So by examining the behavior of the model under various operating conditions, it will then be possible to predict its behavior under actual conditions. Okay. So if you with the mathematical model, we can do the simulation, and using the simulation, we can predict if I apply this amount of force or this amount of torque, how the position and velocity will change. I can do that prediction. Then the second advantage is dynamic model of the robotic system can be used to develop suitable control strategies to achieve the optimal performance under high-speed operations. Okay. So if we have the mathematical model that involves the forces and torques, okay, then I can design the controllers, okay, whether it is a PID controller or whatever state space model based controller, okay, so that can drive the appropriate amount of force and torque and control the operation of the robot. third advantage is if you have the mathematical model, so we will understand what is the amount of force and the moment required, moment of inertia required, and once we know this, we can appropriately do the mechanical design also. Okay, so if you have the mathematical model, you can modify the mechanical design, that what should be the length of the link, okay, what kind of bearing I should use, what kind of actuator I should use, what motor is suitable, okay, what should be the current rating of motor, if I need this amount of force or torque. Okay. So all this information you will get if you have the good mathematical model involving force and torque. However, dynamic modeling of the robot is a slightly complicated process. And we'll see with that some examples. So as we did in case of kinematics, here also we can talk about forward dynamics. That is, if I apply a particular force or a torque, what will be the response? That is the forward dynamics problem. Whereas the inverse dynamics problem is, okay, to achieve certain response or certain position or velocity or acceleration, what should be my force and torque? So that is the inverse dynamic problem. Any question? So usually robotics, we model the dynamics, okay, using what is known as Euler-Lagrange formulation. Okay, so in our control systems course, okay, first we did the mathematical modeling. Okay, so that is called as the Newtonian approach. That is the Newtonian approach. So what is the Newtonian approach? We draw the free body diagram, indicate all the forces that are operating on the body. Okay. Then we say apply force minus opposing force is equal to mass into acceleration. It is the famous Newton's second law of motion. Okay. So that is the net force operating is equal to mass and acceleration. So that is the standard Newtonian approach. So here in the Lagrangian approach, we write the equations in the form d by dt of partial derivative of the Lagrange with respect to the velocity of the joint variable minus partial derivative of the Lagrange with respect to the joint variable position. This is equal to the whatever torque or force that we have applied. So that in a given serial link robot, there will be so many joints. Okay, suppose it has 6 degrees of freedom and it has 6 actuators. Okay, so at each actuator you are applying certain torque, right? So you are using some particular DC motor or what we call as servo motors, and it has particular current rating, etc., and you are basically generating the torque. So at each joint we write this Lagrange equation. Okay. So tau I is the generalized force or torque, and ui is the ith joint variable. Tau I the generalized force or torque at the ith joint variable. Okay. So when you basically apply this torque and your servo motor rotates, accordingly the position or the pose of the robot changes, right? So you have overall pose of the robot is the overall vector of the QI. So Q1, Q2, Q3. So if you take it as that vector, that decides your overall pose of the robot. So for each joint variable, there is an associated servo motor that you are applying the torque, and it is changing the the angle or the prismatic displacement, and you are achieving the certain position for the robot. Now, I use the word Lagrangian. So, what is a Lagrangian? Lagrangian is defined as the difference between kinetic energy and potential energy of the robotic system. So, the final mathematical model will be of the form d by dt partial derivative of Lagrangian with respect to the velocity of the joint variable minus the partial derivative of the Lagrange with respect to the joint variable is equal to torque or the force applied at ith joint, where Lagrange L is defined as the difference between kinetic energy and the potential energy of the overall robotic system. Any questions? Okay. So total kinetic energy in the robotic system is given by K is equal to summation Ki, where Ki is the kinetic energy associated with each link or joint. Okay. So that is the total kinetic energy. Similarly, potential energy. How do we compute kinetic energy associated with ith link or joint? That is given by 1 by 2 mi, okay, mass of the ith link into velocity vector, that is the linear velocity vector Vi transpose into Vi plus 1 by 2 omega I transpose Ii into omega I. So you can verify the units. Kinetic energy is kg half mv square. So that v square that we write in the scalar form is, when it comes to vector form, it's basically quadratic term. We write it as v transpose v. So that is kg meter square divided by second fourth power of second plus 1 by 2 omega transpose. So unit of omega is radians per second. So again we have two omega terms here, and moment of inertia at ith link. That is what is the unit of moment of inertia? Anybody? What is the unit of moment of inertia? the standard Newtonian equation we would write, for the simple pendulum, applied torque minus opposing torque is equal to moment of inertia into angular acceleration. Meter square per second square, that is for the velocity, the linear velocity. For the angular velocity, radians per second into radians per second, because we have two omega terms. So what will be the unit for the moment of inertia?
kg meter square.
Response in the chat box. What is the unit of moment of inertia? Kg meter square. Okay, right. So that will match with the units here. So kg meter square per second square. Kg meter square per second square is the unit of the kinetic energy. Okay. So here velocity vector is velocity along x direction, y direction, and z direction. Then we have angular velocity vector. Again, this is the angular velocity around x-axis, around y-axis, and around z-axis. How it is rotating with respect to x-axis, y-axis, and z-axis. Then II is the inertia tensor of size 3 cos 3. Okay, so like in case of the links, this inertia, moment of inertia is written as an inertia tensor. Okay, it's basically a matrix which is of size 3 cross 3. Okay, about its center of the mass. So this equation that we are seeing is actually a consists of terms involving vectors and matrices. But when you do the calculation, the final result is a scalar quantity. Yes, Ki is a scalar quantity. And again, the potential energy of the robotic system is sum of the potential energies at each joint. So that is given by minus mi Ci transpose into G. Okay. So where Ci is the position vector and G is the acceleration due to gravity vector. So again, C transpose G is a scalar quantity. So the position vector of the center of the mass of that particular link. So that position vector is with respect to the origin. So that we denote it as small ci. So associated with that link, there is a mass mi and moment of inertia tensor ii, and the velocity vector vi, and the angular velocity vector omega I. Okay. So this all corresponds to the link number I. So you do this for each link, and you take the total kinetic energy and total potential energy. Then you take the difference. You get the Lagrangian of the whole system. Any questions? So it will be more clear with the example. So if we consider the single link manipulator, okay. So single link manipulator is basically inverted pendulum, not the inverted pendulum, the normal pendulum. So frame x1y1 corresponds to the origin, frame x2y2 corresponds to the end effector. So C is the center of the link. So if the entire length of the link is A, then the center of the link is at A/2. Then we have the gravitation pointing downwards. So what is the position vector of the link that is given by from the origin? It is from the origin up to the center of the link. It is given as A/2 cos theta, A/2 cos theta, and A/2 sin theta. That is the x position is A/2 cos theta, y position is A/2 sin theta, and 0 along the direction. Okay. So it is rotating around z axis, and the velocity vector is taking the derivative of this with respect to time. A/2 minus sin theta into theta dot, A/2 cos theta into theta dot. Okay. These are all the functions of time. Then the angular velocity vector omega is given as 0, 0 omega z, obviously, right? Because it is rotating around z axis. The x component of the angular velocity vector, x and y component of the angular velocity vector, both are 0. Now coming to inertia tensor, okay. So it is given by diagonal matrix. It's a diagonal matrix, and this inertia tensor is given with respect to body frame and not the origin. This is obtained with respect to the body frame. It is 0 ma square by 12 comma ma square by 12. And inertia tensor with respect to the base frame is given by to the coordinate transformation using the rotation matrix, that is R of t into IB into R of t transpose. Okay. There R of t is equal to Rz of t. That is the rotation matrix with respect to the z axis. So this is basically called as the coordinate transformation. original frame is another coordinate frame, and so representation of the tensor, inertia tensor with respect to body frame. You want to see the representation of inertia tensor with respect to origin frame. You will do R of t by B, R of t transpose. So the rotation matrix is basically, it's like a change of basis matrix. That is it. It is basically changing from one coordinate frame to another coordinate frame. Any question? So what is our goal here? The goal here is obtain the Lagrangian, okay, that is kinetic energy minus potential energy. Okay, in the example of single link manipulator, there is only one kinetic energy term and there is only one potential energy term. And then after obtaining the Lagrange, you will apply this equation in this format to get the mathematical model, dynamics model of the system. So what are the terms we need? We need kinetic energy and potential energy. Kinetic energy is given by half m v transpose v plus half omega transpose I omega, and potential energy is given by m into c transpose into g. So we need to get these terms. We need to get kinetic energy and we need potential energy. So for that purpose, we first obtain the velocity vector, and we will also obtain the angular velocity vector, and then we can write the kinetic energy. So what will be the kinetic energy? The whole system. So first we have this let's go back. M into V transpose V. So this is velocity vector. Okay. So V transpose V, you take the inner product of this V with respect to V only. So what it will be is a square by 4 sin square theta into theta dot whole square plus a square by 4 cos square theta into theta dot whole square. So if you take a square by 4 theta dot whole square, then you can just add the sin square theta plus cos square theta term. So what you are getting with V transpose V, we are getting a square by 4 theta dot whole square plus a square by 4 theta dot whole square. So which is equal to a square by 2 theta dot whole square. A square by 4 because check that. The next term is the angular velocity. So here we have ma square by 12, ma square by 12, and it is along the z direction. So we have this omega transpose I component. So we take ma square by 12 into theta dot whole square. And the potential energy is m into C transpose G. So again C transpose okay. So as per the diagram, the gravitational vector is pointing downwards, that is along the x axis. So the position vector is a by 2 cos theta, a by 2 sin theta, 0. So if you do C transpose G, that is the inner product of C and gravitation, will get only along the x direction, that is a by 2 cos theta into mass. So mg a by 2 cos theta. So minus of that, so plus mg a by 2 cos theta. So that's our potential energy term, and this is our total kinetic energy term. So gravitational force is in the x direction. Next we need to do dou L by dou theta dot, because that is the first term in the Lagrange. Dou L by dou y dot, and then we need to take d by dt of this dou L by dou theta dot. So what is dou L by dou theta dot? It is ma square by 3 theta dot. Okay. So the theta dot term is only in the first term. Okay, there is no theta dot term in the potential energy term. So partial derivative of this second term with respect to the theta dot will be equal to 0. Okay, so only with respect to the first term we are taking the partial derivative. So that will be ma square by 3 theta dot, and then you take the differentiation with respect to time of the above term. So it will become ma square by 3 theta double dot. Then dou L by dou theta. Okay, then you take the differentiation of the Lagrangian with respect to theta. Okay, so in that case the first term will become 0 because there is no theta term in this. There is only a theta dot term. So first term will become 0, and for the second term it will be minus mg a by 2 sin theta. So the final model, dynamic model of the single link manipulator will be ma square by 3 theta double dot plus mg a by 2 sin theta is equal to applied torque. Any questions? Any questions?
No, sir.
Let us go for the second example. Will be little more difficult because we add one more link and we go for the two link manipulator. So again, we can write the center of the first link is L1 by 2. Okay, so the coordinates will be L1 by 2 cos theta 1 and L1 by 2 sin theta 1, and the center of the second link will be what? It will be L1 plus, this R2. R2 is basically L2 by 2. R2 cos theta 2 plus R2 sin theta 2. Okay, L1 plus R2 cos theta 2 plus R2 sin theta 2. So that is the center for the second link. So two position vectors. So we have to calculate kinetic energy for this first link and kinetic energy for the second link. Add, we get total kinetic energy in the system. Again, you compute potential energy at this center of the first link and potential energy at the center of the second link. You make the total, get the total potential energy. Take the difference between kinetic energy and potential energy, get the Lagrangian, then you apply that Lagrangian Lagrange model equation. Position vector of link 1, R1 cos theta 1, R1 sin theta 1, 0. R1 is basically L1 by 2. So then the corresponding velocity vector is minus R1 sin theta 1 dot, R1 cos theta 1 dot, and 0. Just differentiate with respect to time. Then angular velocity vector for omega 1 is 0, 0, omega z transpose. Okay, so therefore kinetic energy for link 1 is 1 by 2 m1 v1 transpose v1 plus 1 by 2 omega transpose I omega. So just as we did in the previous example, so almost the same equations we get for the first kinetic energy term K1. Okay, but here in this single link we showed the x and y direction, it was downwards, but here it is the pointing upwards. Okay. So note the xy coordinate frame. So accordingly, we need to write our potential energy term will be C transpose into gravitation. So gravitation is along the y direction and it's in the opposite direction of the y-axis. So therefore, the potential energy will be M1 G R1 sin theta 1. Okay. Any question? Okay. Then we go to the second link. There are no questions about the first link. Second link, C2 is L1 cos theta 1 plus, okay, right, L1 cos theta 1 plus R2 cos theta 1 plus theta 2. L1 sin theta 1 plus R2 sin theta 1 plus theta 2. So for the velocity, you take the differentiation with respect to time of the position vector, you get the velocity vector, and angular velocity vector is again in the z direction, but now it is theta 2 dot. So V2 is equal to 1 by 2 M2 V2 transpose V2 plus 1 by 2 omega transpose I omega. Okay. So you do V2 transpose V2. And also do omega transpose I omega. So that will be M2 L2 square by 12 theta 1 dot plus theta 2 dot whole square. Okay, so this is the final answer for the K2. Then potential energy for link 2 is M2C2 trans G. Okay, so C2 is the position vector and gravity is in the negative y direction. So you get M2G R2 sin theta 1 plus theta 2. Then you get the total kinetic energy, obtain the total potential energy. Okay, then you write d by dt dou L theta 1 dot minus dou L by dou theta 1 equal to tau 1, that is the torque at the first link, and then d by dt dou L by dou theta 2 dot minus dou L by dou theta 2 equal to tau 2. So that is your second equation. Okay, so you get two equations for two links and joints. So when you do all the derivation, after you take all the differentiation of each and every term, you generally get in this particular format. Okay. So depending on number of links and joints, here in this example you have two links problem. So it's we have two equations. So if you arrange those equations in the vector and matrix format, okay, after taking all those differentiations, you get in this particular format. Okay. So in this format, the first term M is a symmetric matrix. So we say that the term involving force due to acceleration. The second term we call it as the centripetal force. Third term is called as the Coriolis force. Okay, so in the Coriolis force, the terms will be theta 1 dot, theta 2 dot. In the centripetal force, it will be theta 1 dot square, theta 2 dot square. In the force due to acceleration, the terms will be theta 1 double dot, theta 2 double dot. Okay? So you can notice the difference. Theta double dot, theta 2 double dot, that is acceleration. If it is theta dot square, then it is a centripetal force. If it is theta 1 dot into theta 2 dot, we call it as Coriolis force. Okay, that is two velocity of two, both are causing the force. Then finally you may have one gravitational force term in terms of theta 1 and theta 2. So you get in this particular format. So I'll leave that this as exercise for you and obtain in this particular format. So you will have these two equations. You take the derivative of each of the Lagrangian that we have obtained here. K1, K2, P1, P2 we have obtained. You obtain the Lagrangian, take the derivatives, and you write it in this particular format. This discussion, this example is available in many standard robotics textbooks. So with this topic, we come to the close of the discussion on the robotics part. Okay, how to do kinematic modeling, how to do dynamic modeling, how to do simulations, how to represent the position with respect to one frame, how to modify it to another frame. So all this is being discussed with respect to the robotics. Okay. So next few classes we will discuss the computer vision and image processing. That's okay. Only about acquiring the image, how the image is formed, how the image is pre-processed, how do you do feature extraction, all that image processing and computer vision part we will discuss, and then we need to integrate whatever the images that you have taken from the environment, that information how we can use to actuate the robotic links and joints. Okay, so you acquire the information about the environment using the images. You acquire using your camera sensor or whatever. Then based on the information, you have the robot models, kinematic and dynamic model. So you apply appropriate work and force, you design your controller, you actuate the servo motors, okay, and you take the appropriate action. So that is the overall summary of this course. So next class we will start discussing computer vision and image processing. Any question on dynamics? Please study the notes. Okay, do some examples from the textbook. You know, can refer to Niku or one by Saha. If you face any difficulty, you can send me email. We can discuss in the class. Thank you. Have a nice day.
Hello, sir.
Not able to hear the audio due to some reason. So I just type in the chat box if you have anything. Is something wrong with this connection?